welcome back to Miss Sogram's Maths. This video is going to take you through a practice parallel paper on Level 3 differentiation that was written by a colleague of mine who's very experienced in these externals. So all of these questions on this video are very similar to the setup and the kind of questions you would expect on a Level 3 differentiation paper. So that means the first two parts are always worth an achieved point. The next two parts, parts C and D, are worth merit, and the last part of each question, an E, is worth the excellence. Now that can change for the real thing, but they usually follow that same sort of pattern. So let's get stuck in. Now you'll notice as I go through these, on the left-hand side of each one, I've got a couple of notes of the type of thing it's testing you on. I made those notes for my class so they could have a hint after they'd sat the paper the first time round of what each question is needing you to think about and do. So for question 1, we need to do this differentiation using our knowledge of the chain rule and how the trig functions differentiate. So the chain rule tells us to differentiate the outside function, which is the tan function. Now tan differentiates to sec squared, so dy by dx will be a quarter of sec squared, and leave the inside of that function, the 4x alone, don't do anything with that just yet, and then multiply it by the derivative of the inside of that function just there. So we are going to differentiate 4x, that becomes 4. So the quarter multiplied by the 4, they cancel out, so we just get sec squared 4x. For part B, we want to find the gradient of the tangent to the function that we have of f of x here at a particular point. So we need to differentiate f of x and know that when we substitute in, we're using what we know about equations of tangents here. So f dash of x will be, we have actually got the chain rule again here, so the outside function is the bracket. So we would do 2 times that bracket and reduce the power by 1, so that's a little to the power of 1. You wouldn't need to write the 1, I'm just putting it in for this completeness here. So leave the inside alone and then multiply by the derivative of the inside, and make sure you put that in a bracket, otherwise you will get that wrong. So now if we want to find out what the gradient of the tangent is when x is 1, because of this bit just over here. So if x is 1, f dash of x will be equal to, well, substitute into that equation there and we get 2 times by, well, in that we've got 1 minus 1 plus 1 multiplied by 2 times 1 is 2, take away 1, so overall we have 2 as our answer. So that one was worth a U mark, that one was a U mark. This one will be worth an R because it's our merit question for part C. Right, find the values of x for which the function that we have here is decreasing. So if the function is decreasing, that means the gradient is negative. So we need to find the gradient first. So dy by dx is equal to, if we differentiate x, we get 1, minus 1 goes away, and then we need to differentiate 2x to the minus 1. Think about that as being 2x minus 1 to the minus 1, and then apply the chain rule to that. So this would be minus 2, reduce the power by 1, leave the inside alone, times it by the derivative of the inside, which is just 1. So this becomes 1 minus 2 over x minus 1 squared. Now if that's decreasing, we need to know when it will be negative. So set it to be less than 0 and start rearranging. So I'm just going to move that negative 2 over x minus 1 squared to the right hand side like so, and we'll have x minus 1 squared less than 2. which is a quadratic, and we've got to be careful sorting that out with the inequality. So think about it being it's a positive quadratic, and we want to know when does it drop below 2. So we're looking for this point and this point here, and we'll know that in between those 2 points it drops below 2. So if we solve this for equal to 2 first, we will get x minus 1 is equal to the positive and negative square root of 2, so x is equal to 1 plus or minus root 2. So this will be x is 1 minus root 2, and this is x is 1 plus root 2. So it's decreasing between those 2 points. And if you just got the derivative part of that right, this bit just here would have been worth a u if you didn't get all the way through to the end and get the r mark. Okay, for what values of x is the tangent to the graph of this function parallel to the x-axis? So first of all, parallel to the x-axis would be the gradient is equal to 0. So we need to find the gradient of this function. That's going to use the quotient rule because we've got something divided by something else. So f dash of x. Well, u is equal to e to the x. V is equal to x plus 1. You have the quotient rule on your formula sheet, and it tells you that we do v du by dx. So that's x plus 1 times e to the x, minus u dv by dx, so that's just going to be e to the x, and divide it by v squared, x plus 1 squared. Up to that point, getting that differentiation would get you a u. Now we want to set that equal to 0 to find out when that gradient would be equal to 0. So parallel to the x-axis. Now if we bring up the x plus 1 squared over to the right hand side and multiply it by 0, we're going to get nothing. So we've got x plus 1 e to the x minus e to the x will also be equal to 0. And if we take out a factor of e to the x, we get x plus 1 minus 1 equals 0, or e to the x times x equals 0. So either e to the x equals 0 or x equals 0. Well, that's not valid. If you try to solve it, if you try to do log of 0, you will get a math error on your calculator. So x must be equal to 0. Okay, we've got a fairly tricky related rates of change question now. Sand is dropping onto this cone shape and building up this pile of sand that's being modelled as a cone, and we're told a few bits of information about it. So let's step through and see what parts we can write down to be able to make a connected set of things we can do our related rates of change on. So we've got that the volume is increasing at a rate of 10. So dv by dt is equal to 10. In terms of its height, h, the base radius is r, and we've got the volume of a cone. So volume is equal to 3rd pi r squared h. So we've got a way that those things are connected in that formula. We also have another point of connection with them. If we look at this triangle, let me just make that a bit brighter. So if we do this triangle here in our cone, we've got a right angle triangle with a base radius there, a height of h. We've got a set angle of 30 degrees, which means we could work out, if we call this bit here our s for slant height, then we can use trigonometry to link those things together. So r will be equal to s cos 30 degrees, and h will be equal to s sine 30 degrees. Well, cos of 30 degrees is one of our special angles, and that gives us root 3 over 2. So r will be root 3 over 2s, and h, Well, sine 30 is the same as a half, so h will be half s. Okay, then the thing we're being asked to work out is the rate at which the slant height is increasing at a particular point when the base radius is 20. So the rate we want to work out is ds by dt. So this will be equal to dv by dt, the thing that we know about. We've been given dv by dt, so start with that one. And then what do we need to times it by to make ds by dt? Well, we need to introduce s, and we need to divide out the v. So we need a relationship between s and v. Now, the problem that makes it tricky here, we've got a relationship with v between r and h, but not with s. So we need to use these linking formulas here to replace both r and h with their equivalent s's, so that we can have a formula that's linking s and v and differentiate it. Okay, so if the volume is equal to 1/3 pi r squared h, well, that will be 1/3 pi. Well, r we've just seen is this thing here in terms of s, so that will be √3 over 2s squared, and then h is half s. So h in terms of s we got from this over here. So that was using our Pythagoras. Now we do have v in terms of s. And if we tidy that up, we get 1/8 pi s cubed. Okay, so now we can differentiate that. So dv by ds will be 3/8 pi s squared. Remember, pi is just a number, so it doesn't actually do anything with the differentiation other than being a constant in front. Okay, so if we're doing ds by dt, we want to do dv by dt times ds by dv, what we had up at the top, just over here. Okay, so if we replace dv by dt with what we know of dv by dt, which was that it's 10, and ds by dv, well, that will be 1 over dv by ds, because this needs to be flipped over so that we've got ds by dv. Okay, now we need to work it out when r is 20, because that was in the question. We're doing this when the radius is 20. So when r is 20, we want to put that back in terms of s, so we can put it into our formula. So r is equal to √3 over s, so 20 is equal to √3 over 2s. So then if we do 20 divided by √3 over 2, we'll get s is 40 over √3. Now we can put that into what we were working out. ds by dt will be 10 multiplied by 1 over 3/8 pi of 40 over √3 squared. Pop that into your calculator. I would recommend trying to work that through in exact numbers, the bits that you can. Get some calculator help if you need to, so that we can leave this as an exact number at the end, centimeters per second. So it's 1 over 20 pi. Now, if you did do that all on your calculator, you would get a rounded decimal answer, and that would be of 0.0159. That would also be acceptable. And this would get you down to the t mark. Now, if you did some initial differentiating at the beginning, correct, then you would have got a u mark. If you got down to relating some rates together, probably this point here, that would have got you an r. Okay, question 2, back to some easy stuff for part A. So first off, always write those in power form. That's much easier to differentiate. So the 1 goes away, we've got 2x minus 2x to the minus 2 plus 6x to the minus 3. For part B, we are going to find the equation of the tangent to y. For that, we need the gradient to be able to put it into the equation of a line. So using our quotient rule, u is x, v is 1 plus x squared, so dy by dx is equal to v du by dx, so that's 1 plus x squared times 1 minus u dv by dx all over v squared. You can tidy that up, but there is no need. We're going to go straight into working it out. When x equals 1, dy by dx will be, if we put 1 into each of those places, you will actually have that come out as 0. And y will be equal to a half simply by putting x equals 1 into this y equation just here. So now we've got the gradient and a point on the line. So y minus y1, x minus x1 is our equation of a line formula. So y minus a half is equal to 0, x minus 1. So y minus half is 0, or y equals a half is our line. Okay, part C, I really like these questions. They're usually worth a merit point and they're not all that hard to actually wrap your head around, but you do need to be careful about it and know what you're talking about, obviously. So for this function, find the values of x that meet the following conditions. F of x is not continuous. For that we want anywhere where there is a break in the line. That is right here. We have a little hole in our graph at this point here, and that is when x equals minus 3.5. F of x is not differentiable. Now, it's not differentiable anywhere that we have a kink or a hole. So we've got some kinks in the graph just here and here, and also the hole that we have already identified. So it's not differentiable at, first of all, minus 5, when we're looking for this value here, minus 3.5, and this one here is the minus 2. F dash of x is equal to 0. That means the gradient equals 0. Now the gradient will equal 0 anywhere where you have a horizontal line or a turning point, and we've got both of those. So we have our horizontal line here. Now we can't just say it's from minus 5 up to minus 2 because we have that gap in it. So we need to go minus 5 up to minus 3.5. and then minus 3.5 up to minus 2. And then the third place is where we've got the turning point just here, so when x is 0. F double dash of x is greater than 0. So the second derivative gives us what type of local maximum or minimum we have. So if the second derivative is positive, that means we have a local minimum. So we're looking for, on the graph, where do we have a minimum happening, and it's this portion of the graph creates a local minimum. So that bit of graph runs from minus 2 up to positive 2, creating that local minimum. What is the value of the limit of f of x as x goes towards minus 5? So as we head towards minus 5 from both the left and the right, we head towards the same point here, and that value is at this point on the graph, so it is 5. What is the value of the limit of f of x as x heads towards minus 3.5? So it's not what's happening at 3.5, it's what's happening as we go towards it. So from the left, we head towards this value. From the right, we head towards this value. We are heading towards, it's 5 again. So the limit there is 5. It's not the value of the function at that point, it's what's the limit as we approach minus 3.5. Now, if you get 3 out of those correct, then you get an R mark. So 3 out of 6, I think is pretty good going. 3 correct would be equal to an R, 2 correct was equal to a U. Okay, for part D, the hardest part of this question is actually just understanding what it's asking you about. The calculus itself is not that tricky. So find the value of k so that the tangent to this curve here, 4 over x, so the tangent of this curve, we're talking about this line here, when x is 3, so this tangent, and the tangent to y equals x squared, when x is k, is perpendicular. So how can we make this line here meet at a right angle? So be perpendicular just there. And if they're perpendicular, the product of their gradients is -1. Let's start by finding the gradients of those tangents. So y dash of the first one, so if y was equal to 4 over x, that's 4x to the -1, dy by dx would be equal to -4 x to the -2. Now, if y is equal to x squared, dy by dx is equal to 2x. So we've now differentiated both of those equations. When x is 3, we're looking at this equation here, then the gradient of that line, so let's say gradient 1, it's going to be this line here, so it's this gradient equation here. So -4, 3 to the -2. Well, that equals -4 over 9. Okay. When x is k, the gradient that we're looking for, gradient 2, so this one here is this equation here, that will be equal to 2k. Now, if they're perpendicular, it means that those two gradients multiplied together will equal -1. And if you rearrange to solve that, k has got to be 9 over 8, or 1.125. Okay, the excellence part of this one. We're using product rule and differentiating e. We've got a curve defined by this here, and that's where we've got the product rule comes in. It's got x multiplied by a function of e. Find the x coordinates where the gradient is equal to this. So let's first of all start by differentiating f of x. And for the product rule, we're going to differentiate x, times it by the original of the other one, and then do that the other way round. So if we differentiate e to the x minus k squared, we've got a chain rule within a chain rule. That becomes 2x minus k e to the x minus k squared. Okay, so tidy that up. We've got e to the x minus k squared, 2x, plus 2x x minus k e to the x minus k squared. Now we want to set f dash of x equal to this bit here, e to the x minus k squared. And we've got to try solve that. Now it looks horrendous. It's not actually all that bad because we can divide through by, oh, I missed a bracket there, e to the x minus k squared. So if we divide through by each of those, we can divide there, divide there, divide there, and we're just left with a 1 and a 1 on that side. So we end up with 1 plus 2x x minus k is equal to 1. So 2x x minus k equals 0. And so x is 0 or x is k. Okay, so on to question 3. We need to differentiate y equals ln x over x. We are using the quotient rule and knowledge of natural logs. So that means we will do, dy by dx will be v du by dx. So the bottom one times by the derivative of the top minus the top one times the derivative of the bottom all over the bottom one squared. You don't need to simplify for your marks on achieved, but I will do anyway just because that looks horrible and it's got an easy simplification. So 1 minus ln x over x squared. For part B, we've got this equation of a curve. Show that there are no turning points on the graph of the curve. So y equals x minus 5 to the half. If we were looking for turning points, dy by dx would be equal to 0. So dy by dx, using the chain rule on this, it would be half, and then reduce that power by 1, and times it by the derivative of the inside, so we're timesing by 1, so that's not going to change anything. Now, if we set that equal to 0, then we get this. And if you try to solve that, you'll see that that becomes something impossible. And if there are no solutions to that equation, then there's nowhere on the graph where the gradient is equal to 0, therefore there are no turning points. Okay, parametric equations for part C. So a curve is defined parametrically. Find the gradient at a particular point. So we're going to differentiate x with respect to t, which would be minus 4 sine 2t, because cos goes to minus sine, and then we would multiply it by the derivative of that inside 2t there, so you end up timesing it by 2. And then dy by dt is equal to, well, remember that this is actually cos t all squared, so we use the chain rule on that, so it's 2 cos t to the 1 multiplied by the derivative of the inside. That's minus 2 cos t sine t. Now dy by dx will be dy by dt times dt by dx. So that'll be our minus 2 cos t sine t all over minus 4 sine 2t. We could simplify it, but there's no need. Now we need to find when t is pi by 6, dy by dx will be, and put pi by 6 into this equation of dy by dx that we have, and that will come out quite nicely on your calculator as 0.25. Just make sure your calculator is in radians mode, because the value of t that we've got there is in radians. Now this one would be an R mark. If you did some correct differentiation earlier on, you'll probably get the U mark somewhere along the way there. Okay, find the equation of the normal to this curve x cubed ln x. So we've got two things being multiplied together, so we know we're going to need the product rule there at the point when x is equal to e, and remember e is just a number. So if y equals x cubed ln x, then u is x cubed, v is ln x. We're going to use the product rule, so we get 3x squared dv by dx 1 over x, so dy by dx equals u times dv by dx plus v times du by dx. Now when x is equal to e, we'll substitute that in for dy by dx. So x cubed over times 1 over x, it simplifies to x squared, so this will be e squared. Ln of e is 1, because they are inverses of each other, and that'll be 1 times by 3 times e squared. So we have e squared plus 3e squared, so that's 4e squared. Now we want the equation of the normal. So that's the gradient of the tangent. So gradient of normal will be minus 1 over 4e squared. And the final piece of the puzzle we will need is the value of y. So if x is e, we pop that into the equation x cubed ln x. So that will simply be e cubed, because ln of e will be 1. So now y minus y1 is equal to m x minus x1. So y minus e cubed is equal to minus 1 over 4e squared x minus e. You could multiply out, rearrange, simplify if you want. However, that will be sufficient to get you the r. Okay, finally, we've got related rates of change on this cylinder that's within a cone. So the top of the cone and the cylinder, they have the same circle bit that they have at the top. The cone has got a total height of 18 and the radius of 3. Now we need to work out the height to be able to maximize the volume. So we need a formula for the volume so we can find the maximum of it. So the volume of the cylinder is pi r squared h, where this is going to be r, it's the radius of the cylinder itself, and let me just draw that on here actually. There's the r, and the height of our cylinder would be here. And what we intend to do is differentiate it, set it equal to 0, so we can find the maximum on that curve of the formula for the volume. The problem is we can't differentiate this when it's got 2 variables in it. We need to find the relationship between r and h so that we can express one in terms of the other. Now, if we look at the portion of the cylinder where we know that that's a 3 across there and that's an 18, we know that as the height of the cylinder moves up and down, it will still create those similar triangles. So if we take this over to one side, like so we can see that a little better, we have the relationship where the radius is equal to, if we times it by 6, it will equal the height. So if we wanted to work out this height here of h that we needed, h would be, or this piece left would be 18 minus this section here. Well, that section is, if that's r, this is equal to 6r because of similar triangles. So this smaller triangle here would be 6r and r. So this piece there would be 18 minus 6r. So in our volume formula, we can change the h to be 18 minus 6r. And if we multiply that out, we get 18 pi r squared minus 6 pi r cubed. Now, if we want a maximum of that, we need to differentiate. So differentiate with respect to r. We can now differentiate because we've only got r's in our formula. So we will get 36 pi r minus 18 pi r squared. And we know that maximums or minimums happen when we set the derivative equal to 0. And now we're going to try and solve that. So if I factorize out as much as we can take out 18 and we can take out pi and we can take out an r. We would get 2 minus, and then we're just missing an r there. Okay, so either 18 pi r equals 0 or 2 minus r equals 0. Well, if 18 pi r equals 0, then r would be 0. If 2 minus r was 0, r equals 2. Well, the radius can't be 0 to make a maximum volume, so that's not feasible in our context. So therefore, this is our solution. The radius must be 2. Now the question itself, just go back and check we were asked what height must the cylinder have if its volume is to be maximized. So maximum volume, max volume when radius is 2 centimeters, and the height, we know the relationship there is that the height is 18 minus 6r. I'll rewrite that as 6 times 2. So 18 minus 12 is going to give us 6 centimeters for the height of the cylinder there.